NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we solve quadratic equations that involve the floor function. We will turn the floor function into an integer variable, solve a simple quadratic, and then map the results back to x as intervals. Start with the general form. Let k be the floor of x. Then we just solve an ordinary quadratic in k. Step 1. Check the discriminant. Compute delta equals b squared minus 4ac. If delta is negative, there are no real roots for k, so the original equation has no solution. Step 2. Solve for k. Use the quadratic formula, but remember, k must be an integer. If a root is not an integer, we discard it. Step 3. Map each valid integer k back to x. Because k equals the floor of x, that means k is less than or equal to x, and x is less than k plus 1. This gives a closed dot on the left and an open dot on the right on a number line. There are useful special cases. Case A, if a plus b plus c equals 0, then one root is always k equals 1. The second root is c over a if that is an integer. Case B, if b equals a plus c, one root is negative 1. The second root is negative c over a if that is an integer. Case C, if b equals 0, then a times the floor of x squared plus c equals 0. If ac is positive, there is no solution. If ac is negative, the floor equals plus or minus the square root of negative c over whenever those are integers. Case D, if c equals 0, then the floor of x times a floor of x plus b equals 0, giving either floor of x equals 0 or floor of x equals negative b over a if that value is an integer. In this lesson, we will solve a quadratic equation that involves the floor function, written as square brackets x. Our goal is to follow a clean, reliable algorithm to find all x that satisfy the equation. Here is the problem. We will treat the expression inside the square brackets as the floor of x. The equation is 3 times bracket x squared minus 5 times bracket x plus 2 equals 0. Step 1. Replace bracket x by a single variable to reduce the equation to an ordinary quadratic. Let n equal bracket x. Then the equation becomes 3n squared minus 5n plus 2 equals 0. Now apply a quick check. For a quadratic, n squared plus b, n plus c equals 0. If a plus b plus c equals 0, the two roots are 1 and c over a. Let's verify the sum of coefficients. 3 minus 5 plus 2 equals 0. Perfect. So the two candidate values for bracket x are 1 and 2/3. Step 2. Evaluate the first case. If bracket x equals 1, then by the definition of the floor, x must be greater than or equal to 1 and strictly less than 2. So all real x in the interval from 1 inclusive to 2 exclusive satisfy this case. Step 3. Evaluate the second case. If bracket x equals 2/3, recall that the floor function always returns an integer. Since 2/3 is not an integer, this case is impossible and contributes no solutions. Therefore, combining the results, the complete solution set is all real x from 1 inclusive up to 2 exclusive. In interval notation, that is bracket 1, 2 parenthesis. Recap. Let n equal floor of x to reduce the equation to a simple quadratic. Use the sum of coefficients trick to quickly find the two candidate values. Then, apply the floor function definition to translate bracket x equals 1 into the interval from 1 to 2 and discard any non-integer candidate values such as 2/3. Example. In this lesson, we solve a quadratic floor or bracket equation exactly following the given algorithm. The problem is floor of x squared plus 3 times floor of x plus 2 equals 0. Step 1. Identify coefficients and apply the property. Here it equals 1, b equals 3, and c equals 2. We check the property b equals a plus c, that is 3 equals 1 plus 2. Since it holds, the algorithm tells us the roots for floor of x are negative 1 and negative c over a, which is negative 2. Step 2. Solve for the floor values and convert them to x ranges. By the floor definition, if floor of x equals n, then n is less than or equal to x, and x is less than n plus 1. For floor of x equal negative 1, we get negative 1 is less than or equal to x, and x is less than 0. For floor of x equal negative 2, and negative 2 is indeed an integer, we get negative 2 is less than or equal to x, and x is less than -1. Let's visualize both intervals on a number line. We will shade the interval from -2 up to -1, open at -1. Then we shade the interval from -1 up to 0, open at 0. Notice together they form one continuous interval from -2 up to 0, open at 0. Step 3. Combine the intervals for the final solution. The union of -2 to -1 and -1 to 0 is -2 to 0. Therefore, the solution set D equals the interval left bracket -2, 0, right parenthesis. In this example, we will solve the equation open bracket x close bracket squared minus 5 times open bracket x close bracket plus 6 equals 0 using a clean step-by-step algorithm. Step 1. Substitution. Replace the floor of x by a simpler variable y. Then the equation becomes a regular quadratic in y. Step 2. Factoring. We look for two numbers that multiply to +6 and add to -5. That pair is -3 and -2, so the quadratic factors as. Step 3. Solve the factored form and translate back to x. Setting each factor to 0 gives y equals 3 or y equals 2. Now interpret the floor function. If the floor of x equals n, then x lies from n up to, but not including, n plus 1. So for the first case, the floor of x equals 3 means 3 is less than or equal to x, and x is less than 4. For the second case, the floor of x equals 2 means 2 is less than or equal to x, and x is less than 3. Let's visualize these two intervals on a number line. Step 4. Take the union of the two adjacent intervals. The interval from 2 to 3, union the interval from 3 to 4, merges into one continuous interval from 2 up to, but not including, 4. So the complete solution set is x is in the interval 2 to 4. Recap. Substitute the floor by y. Factor the quadratic. Translate each y value back into a floor interval for x, and then take the x is in the interval 2 to 4. Recap. Substitute the floor by y. Factor the quadratic. Translate each y value back into a floor interval for x, and then take the union. That yields the final interval from 2 to 4, not including 4. Final interval from 2 to 4, not including 4. In this lesson, we will solve a floor bracket equation using a classic identity, sometimes called Hermite's identity. The problem is to solve the equation open bracket x plus 1/2 close bracket plus open bracket x close bracket squared equals open bracket 2x close bracket plus 2. Here, square brackets mean the floor function, the greatest integer less than or equal to the number inside. Step 1. We use Hermite's identity for floors. The floor of 2x equals the floor of x plus the floor of x plus 1/2. We substitute this identity into the right side of the equation. Since the same floor term appears on both sides, we subtract it from both sides. That leaves open bracket x close bracket squared equals open bracket x close bracket plus 2. Move all terms to one side to make a quadratic in the floor of x. Let y equal the floor of x. Then the equation becomes y squared minus y minus 2 equals 0. This factors as left parenthesis, y minus 2 right parenthesis times left parenthesis, y plus 1 right parenthesis equals 0. Therefore y equals 2, or y equals -1. Now translate back to x using the definition of the floor function. If the floor of x equals 2, then 2 is less than or equal to x, and x is less than 3. If the floor of x equals -1, then -1 is less than or equal to x, and x is less than 0. Let's visualize these solution intervals on a number line to make the answer intuitive. We will shade the interval from -1 to 0 with a closed dot at -1 and an open circle at 0. Then we will shade the interval from 2 to 3 with a closed dot at 2 and an open circle at 3. Therefore, the complete solution set is the union of the two intervals from -1 to 0, not including 0, and from 2 to 3, not including 3. Example. In this lesson, we will solve the floor equation x squared minus floor of x minus 2 equals 0. We will proceed step by step using a precise case analysis on the integer part of x. Step 1. Substitute the floor function. Let n be equal to the floor of x, an integer. Then the equation becomes x squared minus n minus 2 equals 0. Step 2. Solve for x in terms of n. From x squared minus n minus 2 equals 0, we have x squared equals n plus 2. So x equals plus or minus the square root of n plus 2. Since a square must be non-negative, we also require n plus 2 at least 0, which means n is greater than or equal to negative 2. Step 3. Apply the definition of the floor function. If n equals the floor of x, then n is less than or equal to x, and x is less than n plus 1. We will combine this with our formulas for x to restrict the integer values of n to test. Step 4. Determine the integer domain for n. First, from n less than or equal to x, if we try the positive branch x equals the square root of n plus 2, then n less than or equal to square root of n plus 2. For non-negative n, squaring gives n squared less than or equal to n plus 2, or n squared minus n minus 2 less than or equal to 0. Factoring, we get n minus 2 times n plus 1 less than or equal to 0, which holds for n between negative 1 and 2 inclusive. Checking the negative or small values also supports that the relevant domain to test is n in the set negative 1, 0, 1, and 2. Note that n equals negative 2 fails the floor check because it would force x equals 0, but floor of 0 is 0, not negative 2. To make the interval checks visual, let's draw a number line and highlight the bins for n equals negative 1, 0, 1, and 2. We will test each n by solving x squared equals n plus 2, and then keeping solutions only if x lies in the interval from n to n plus 1. Case n equals negative 1. The interval is from negative 1 up to 0. Substituting n equals negative 1, we get x squared equals 1. So x equals plus or minus 1. Only x equals negative 1 lies in the interval from negative 1 up to 0. So x equals negative 1 is accepted. Case n equals 0. The interval is from 0 up to 1. Substituting n equals 0, we get x squared equals 2, so x equals plus or minus square root of 2, about 1.414. Neither value lies in the interval from 0 to 1, so we reject this case. Case n equals 1. The interval is from 1 up to 2. Substituting n equals 1, we get x squared equals 3, so x equals plus or minus square root of 3, about 1.732. The positive root lies inside the interval, so x equals square root of 3 is accepted. Case n equals 2. The interval is from 2 up to 3. Substituting n equals 2, we get x squared equals 4. So x equals plus or minus 2. Only x equals 2 lies inside the interval, so x equals 2 is accepted. Final answer. The solution set is the numbers negative 1, square root of 3, and 2. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.